I suppose to some extent I was crafting my mind from an early age, working on physics problems to lead me to work on engineering problems. I definitely have a more creative side in problem solving from having started out in studying physics. You start getting into general relativity and different manifold spaces. You just have to think about problems differently to understand them.
Hello and welcome to the Being an Engineer podcast. Today we're joined by Rod Scholl, Founder and Principal Analyst at Epsilon FEA. Rod has spent nearly 3 decades helping companies solve complex engineering problems using advanced numerical simulation and FEA tools. From turbine engine components at Honeywell to leading high-level analysis projects for Fortune 500 companies, Rod has built a career at the intersection of deep technical rigor and practical business impact. He's not just running simulations, but he's helping companies make smarter engineering decisions. Rod, thanks so much for being with us today on the show.
Great. Thanks for having me.
Yeah. So Rod and I actually used to work together a long time ago, although we kind of ran in different circles. You were part of the simulation group and I was part of the PD group. And so we never really got a chance to get to know each other way back then, but it's funny how things come full circle, right? 20 years later.
Yeah, for sure. I have more associations with your name than your face, honestly. When I see your name, it conjures up our work experience overlap. But
Yeah, right. All right. So, Rod, we're going to start with some rapid fire questions to help the audience get to know you really quickly. Don't spend too much time thinking about the answer. Just share the first thing that comes to mind. So the first one, who do you think is the most underrated engineer of all time?
you're testing my history. Good golly. I don't know history that well. I have to go back to experience of coworkers that I've worked with when I was younger. And at the time, I didn't really understand how much I was learning
Yeah.
from those individuals. I probably shouldn't say personal names. But people I
Fair
worked
enough.
with at Honeywell at the time were understated, and just a
Mm,
few comments is enough to
sure.
make me later realize what depth there was in their skills.
Yeah. Okay. Whiteboard or spreadsheet?
Spreadsheet.
Would you rather prevent failure or design for recovery?
Oh, prevent failure.
And if you could redesign one everyday object, what would it be?
Oh, good golly. My workstation.
What's your workstation like right now?
Oh, it's normal. I got a set stand and everything else. I sure would be nice to just be able to transport to a virtual reality experience that didn't take extra eye focus and could type virtually. It'd be nice to get rid of a mouse and a keyboard.
Have you tried any of the VR tools?
I have. I don't know that it's made me any more productive.
Not really ready for prime time, huh?
Not in my opinion. I had a friend try it out for a while. He was sold, so I let him be the forward exploration. And after a few months, he gave up on it. So I'm like, all right, just save myself a few months.
What's the Apple one called? The Vision Pro, I think. Is that what it's called? It looks so cool, but I struggle to understand like what's really the practical application of it, you know?
Yeah, I mean, at some point I have 3 desktops open, and when I worked in Linux, it was nice to have like 8 different desktops, and you could organize even ideas spatially. Any extra organizational tools helped me do my job. So if I could have a room, to walk in between and move things around, it would be great. But I just haven't gone down that road yet.
Maybe someday. Okay. Well, I'll start with the first formal question of our discussion today that I ask everyone. What made you decide to become an engineer?
Yeah, I didn't read through all the lists, but I did see that one, and I'm like, oh, it's not a great answer. Someone told me I should. I wanted to be a physicist, and they're like, oh, that's a waste of time. You should be an engineer. And I was 18 years old, so I'm like, okay.
That's funny. I laugh because I have a very similar story. I didn't even know, I didn't have any answer to that question. And my dad was like, "Ah, you should consider engineering." Okay, that was about all the thought I gave to it.
Yeah, that's just definitely how it works.
Yeah, when you're, 17, 18, you don't know very much about life, and at least I didn't back then. All right. Well, let's talk about your company, Epsilon FEA, that you founded back in 2000. Was it? I have 2008 here, but I feel like that. I thought you were
Yeah,
still working at the company where we both worked past that.
I was doing work for them, but no, 2008 is when we first started out.
Maybe that's what it was. You were just doing work for them. Okay. So let's talk about that a little bit. How did you decide to go off on your own and start a business doing simulation work?
Oh, I suppose the short answer is at the time I thought, oh, I can make a lot more money doing this by charging the full, hourly rate and increase my take home.
Hmm.
So I think it was just greed and ambition uh,
Or
that
good sense. I
kicked
mean,
it
there's
off.
nothing wrong with that.
For sure. And well, I had enough of a sense of it was something I wanted to do. It sounded fun, and I could do it with the support of the employer I was with at the time. So it was kind of a natural transition.
Nice. And without getting too personal, how accurate were you that you could just make a lot more money by doing it yourself? Was it that simple, or did it come with its own set of complications?
Oh, they were dark days. I started the company, and about 1 month later was the financial crisis of
Oof.
2008, and I'd gone probably a decade without a gap in work up until that month, and then after that, like the whole industry flatlined.
Wow.
So it was like coming into the boxing ring, ready to show my stuff, and it was like the first hit. Everything changed.
Everyone has a plan till they get punched in the mouth, right?
Exactly. So that's
Uh,
basically how it went. But I learned a lot.
what were some of the things that you did to keep your business afloat? And you mentioned learning a lot. What were some of the key takeaways from that time?
I network with people. I'd moved to locations, and I just went out and started meeting other engineers. We started a technical seminar, like a users group for
Hmm.
Ansys in particular. And now we host those about annually, supposed to be more often, and probably 40, 50 people attend. But I remember the first one I had, there were 3 attendees, and that's counting me. So I just kept working that same strategy of giving away free technical information and building context.
That seems to be a really good formula, is giving away good free content to build a reputation and trust. And then once people know you and like you and trust you, it becomes much easier to just reach out and start engaging commercially.
Agreed.
Yeah. Let's talk for those who might be listening and maybe they're not super familiar with what simulation is. Can you talk at high level? What is simulation? What are some of the primary tools that you and your team use?
Yeah, simulation is a big category. Specifically speaking, we're talking finite element analysis and CFD. And if we even have non-engineers in the audience, I would say, see pictures of, piece of structure and it's bending and it's painted different colors and red is where it's going to break. That's the short communication of what we do.
And
Uh, pardon me.
CFD stands for
Oh, computational fluid dynamics. It's roughly the same tool set, only it's on fluids rather than on solids.
got it. Yes. Uh, there are a lot, but can you quickly name a few of the use cases or applications for simulation? Why do people use simulation at all?
Yeah, at some point, as I thought philosophically about simulation, as soon as we're beginning to do mathematics to some extent, we're simulating how many apples we end up with if you give me 4 times 7. And when you do a beam calculation by hand, it's a type of simulation. And generally now the tools have just automated calculations. we're not doing any, everyone's inverted a matrix by hand if you made it through engineering school, and hopefully it wasn't too large. So all the tools really do is build that matrix and then invert that matrix. The actual effort, thinking, and engineering is the same whether you're inverting that matrix by hand or not. The same thoughts go into the boundary conditions, the materials, the inputs, the decisions, what you want to get out of the choice.
Can you run us through the process of setting up a basic simulation? You mentioned things like boundary conditions. What does that mean practically?
Yeah, the mechanics of doing the simulation is not what it looks like when we sit down to work each day, but the mechanics are as a matter of usually starting with someone else's geometry or one that you've created, and choosing what physics you want to come out of it. Oftentimes that is stress. When something's going to break, how much it'll bend, how hot it'll get, what the pressure drop will be as fluid flows through a particular cavity. So you sit down and make choices of what physics do I need to use to answer my questions. And then the next step is, besides materials and geometry, all the rest falls into the category of loads, which is essentially boundary conditions, forces, deflections. How am I going to hang on to it? How am I going to heat it up? Those are all the numerical inputs that are going to go into it. And hopefully you're forecasting the outputs. What numbers am I expecting to get out?
Yeah. You mentioned that early on you were interested in becoming a physicist, and someone suggested that you consider engineering instead, which you did and became an engineer. To what extent did that early interest in physics influence your career path into a pretty physics heavy side of engineering, simulation?
Oh, I suppose to some extent I was crafting my mind from an early age, working on physics problems to lead me to work on engineering problems. I definitely have a more creative side in problem solving from having started out in studying physics. You start getting into general relativity and different manifold spaces. You just have to think about problems differently to understand them. And that might have been a strength from early on, that to question assumptions, look for new ways to examine tough problems rather than turn the crank type analysis.
Let's talk about some of the primary tools that you and your team use. Ansys is probably the big one. Is that accurate?
For sure.
And Ansys is kind of the giant gorilla of the simulation tool set out there in the industry. And it's not an inexpensive program. I don't know. I haven't priced it out anytime recently, but I'm guessing it starts at 10 grand or 15 grand, something like that, and goes up from there depending on what configuration you want. But the point is, it's not an inexpensive tool to purchase. And I have a feeling that there are probably a lot of companies out there who have these tools in-house, but don't really know how to use them. What you've worked with a lot of engineering companies before doing the simulations. Where do you find that companies get stuck? Where are they struggling to really extract value from their simulation tools?
Generally speaking, it's usually the knowledge of the operator that creates the limitations. I've been involved in the sale of Ansys through partnerships and employment for a long time, so I've had some time to think about it. And my biggest sales pitch for Ansys is that it's a tool that scales. If you want to add fatigue to it with that kind of accuracy, you can do it. If you want to add HPC, you can do it. If you want to add abrasion, evolution, you want to do multi-physics, no matter where you get, yes, there's a tool, and maybe it's less refined and more laborious because not everyone's using it, but you'll never reach the point in your tool that you say, oh, my tool can't model this physics. It can always be modeled at a price. And the
Hmm.
real one of the high costs of doing simulation or engineering in general is if you get 3/4 of the way through a problem and then have to change tool sets, it's often like starting over
Hmm.
and then learning. So the cost of Ansys is a lot, but it's also worth it to avoid even one time where you have to mid-program switch tool sets.
Got it. Yeah, that's a great insight. Um, oh shucks, I had a great question in mind and I just forgot what it was. Let's see if it comes back to me.
I'm talking so much, I'm forgetting your question by the time I'm halfway through answering. I'm not even sure I'm answering your question.
That's okay. It's all good stuff that's coming out, regardless if it answers the exact question or not. But I think you have been. Yeah, I can't remember what it was. All right, so we're just going to move on here. At what point, this question could be asked about a lot of specialty disciplines, but applying it to simulation specifically, at what point should companies, like what's the tipping point where a company should bring simulation in-house and just do it themselves versus outsourcing to someone like you or Epsilon?
Yeah, it's a great question. And generally, I would say that it's not two different categories. Everybody should be constantly pushing the technological boundaries as they become available and cost effective for them in their business climate. And it always makes sense to bring in somebody who's already done it whenever possible. You can off if the hourly rate's a little more. It isn't always. A lot of times, people will sell expertise at even below your internal burden rates. To bring that expertise on and always have a partnership where lessons learned are being transferred internally. Not every industry lends itself to that model, but we've been able to do that at Epsilon to a large extent. Anything we learn, we pass on to the customer. Any tricks of the trade, we pass on to the customer. And we're able to do that and stay in business because it's an evolving field. It's evolving, for like Moore's law of processor speed. So I can give away everything I knew 3 years ago and still be guaranteed work because there's 3 years worth of new techniques that are constantly arriving. So
Terrific.
if you have a partnership with people that share all their knowledge and lessons learned, you can march forward together and be increasing internal capacity. Once it's done once and you have a model, if you can arrange to get the database from them, always train somebody in-house to walk in the footsteps of who you're partnering with externally.
I love that mindset. I share it. I always want to give away our best stuff. To me, that just feels like the right way to do business, and it generates trust and reciprocity, and overall, just I think works really well. I did remember the question that I was going to ask you before. To the extent that you can share, of course, without breaching any confidentiality, what is the most technically challenging simulation that you have run? Can you remember?
Sorry, it's late for us. Oh man. Mm, everything is, even when something's not technically challenging, then we're challenged for speed and budget.
Hmm.
There's nothing we do which is generally that easy. If it's easy, then we're like, hey, can we do it in less time? There's definitely times when you hit something in a tool where you can't figure it out. And I had one case, I was trying to simulate evaporation, which I didn't know anything about evaporation, but I took on the work and could not get the tool to give an answer. And I complained to everyone who would listen for a couple of weeks, and I got more and more desperate, thinking, why did I take on this work and say I could do it? Like at some point you're contractually obligated to do what you said you were going to do.
Yeah.
And it was late at night on the internet, 2 a.m. or something. I ran across a random website with like a green background and just HTML text on it. And it says, if you are having trouble implementing evaporation in this particular way, I will sell you the solution for $2,500. No name, just like a PayPal site. There literally wasn't a name. It was like an
Not
LLC.
sketchy at all. Yeah.
Not sketchy at all, but the text in it made me think this person knows what I'm running into. And I
Wow.
think I gave it another day, or maybe I woke up in the morning 8 hours later and I spent $2,500 and got a ACT module, which I plugged into the tool and it worked.
No way.
It did. In fact, I eventually got to know the persons. I've worked with them many times. I've hired them. They've built other tools for us. They're just a very smart individual who found a hole in the tool set when he did the work, patched it, and I might have been his only customer on that particular module. I don't know,
That
but he
is
saved me.
hilarious. Wow. What are
Yeah.
the chances that you come across this site that sounds like it was built in 1998 and just has the exact information you need for $2,500, but hey, it
Yeah,
is what it is.
right.
Hilarious. Okay, so when is simulation not the right tool?
It's not the right tool if people don't know what they want to learn from it. And maybe I'm answering a slightly different question of how a simulation used wrongly. Oftentimes people don't understand a lot about their product or how it's going to perform, and the response is, well, let's simulate it and then we'll learn about our product. And that's an expensive and often unsuccessful approach. You want to know what you're going to do with the answer. And so oftentimes I'll say, okay, if I simulate it and come back with 37 KSI or zero point zero 0.07 inches, what are you going to do with that knowledge? And if they can't answer, like, well, we don't really know what amount of deflection we can
Hmm.
afford, then I'm like, then why model the deflection if you can't use the answer? You're not going to gather information. It's not like real world testing. You're not. Once in a while, we model it just to see what there's insights. That's people with money to burn, and they're in a new domain. They just want to see it. But in 90% of the cases, it doesn't make sense to proceed unless you know what you will do with a numerical answer.
That reminds me a lot of something completely different, but the principle is the same. We do a lot of this. You do a lot of this as well. Quoting. A customer comes to us and wants us to quote something. And for us, I'm sure it's the same for you. It's not a trivial process for us to quote a project. It takes oftentimes tens of hours to put a basic quote together. And we'll always ask up front, we might not use these exact words, but effectively we're asking, what's your budget? Like what can you justify spending on this, and how are you making the decision for whether the investment is justifiable? And so many times customers will be like, well, I don't know. I don't know what we can spend on this. I don't know what the commercial value is. And I'm always like, well, if you don't know what the commercial value is, why are we even going down this exercise right now? It's just like you said, it's wasteful. It wastes time, and it's not an effective process. But it is what it is, and we work with it.
Yeah, that might be good advice. I've never come right out. I've never really had the courage to be like, hey, what can you afford? Like, what's your budget?
Well,
I've always assumed that's a bad strategy.
we don't phrase it exactly like that. I Okay, what I do actually say is something to the effect of, these projects always come down to an ROI. You have to justify it on your end, and we find that if we can have that conversation up front, it often saves a lot of time on the back end. So, what's the commercial value to your organization of having this solution? And we have a little calculator that we use to quickly estimate what that commercial value is, because a lot of times people we're talking to legitimately might not know. So we have a little tool that we use to help, estimate. Sometimes it works, and sometimes people are like, yeah, I don't want to have that conversation. Just give me a quote. But
I hear you. And most of the work we do, the ROI on simulation is huge. Or we talk ourselves out of work pretty early on. It's usually not kind of borderline. I
mm,
think we're doing the same strategy. The way that I often ask questions in the beginning is, well, what happens if it breaks? Is the question. They want to simulate something, and
great.
I'm like,
Yeah.
what happens if it vibrates and does crack? And I'd say more than half the time, someone will say, "No, we can't have it crack. We need to make sure it doesn't crack." And I'll just be like, "Yeah, but what happens if it does?"
Yeah.
And it's surprising. I will have someone suddenly speak up that's been quiet for half the phone call and say, "Well, if it," and they'll explain the entire business case, and I'll often find out that's the senior leader in the room who's already thought about what happens in worst case scenarios. What it does to brand damage or winning the next phase of the project, and sometimes the answer will come back, "Oh, not that much." And I said, "Well, then just test it and try it out. Why pay a bunch of money if it's not that big of a deal? Then you can recover it." And that's how you find the periphery, the boundaries of the particular problem. So you know what's cost effective to then propose as a solution.
Yeah. That's a great way to do it. It's not what's your budget. It's what happens if this thing fails. I love that. Great way to do it. Yeah. All right. Let's see. You spent some time working on turbine engines. at Honeywell, I think.
Yeah.
What did you learn about the relationship between analysis and real world hardware during that time?
Oh, probably not a lot on that subject. I was, I remember the average time at the department I worked in, let's say 15 individuals, the average time in that department was something like 15 years, and the average time at the company was something like 28 years.
Wow.
Talking average.
Jeez.
And I'd come in and basically most of them wanted nothing to do with me. They felt burdened by this, young individual. So they put me on special projects. They put me on the most advanced technology programs they were, and I learned so much because on those projects I had to do secondary flow, I had to do rotor dynamics, I had to do tie shafts, I did burst, I did thermal, I did so many things. To some extent, I robbed them blind because they let me dabble in everything. So I learned a ton of physics and a ton of engineering from their well-documented books, spiral books this thick. My desk was filled with them, and I just absorbed knowledge.
Wow.
It was all written down, and it's not in my textbooks at the time. The textbooks were written based on these spiral-bound books.
Man, what great preparation to become the subject matter expert.
It was a huge opportunity. I didn't enjoy it at the time or maybe even appreciate it, but to this day, I frequently go back and say, "Oh yeah, I know how to do that," but I realize that's because I learned it during that 2-year period at
Wow.
Honeywell
Yeah.
and Allied Signal.
Amazing. For engineers who might be listening to this and thinking, we need help with simulation. Maybe they do some internally, maybe they just need more bandwidth, maybe they don't do it at all, but they know that they need to engage with someone. What can they do to be best prepared to engage with an external resource that's going to support their simulation needs?
Oh, prepared in terms of preparing the problem or prepared in terms of finding somebody.
Preparing the problem.
Yeah.
Although it would be interesting to hear you speak on the latter as well.
Yeah. Preparing the problem, we've kind of covered to some extent, knowing what the, actionable intelligence is. What exactly are they going to do with the information? Break it down to choices A and B. We'll change to this material or that material. Not we'll change the material, but what material will you change through? Think through the problems. When I quote a job and I break it down to a pretty fine detail. I get to the point that I'm imagining looking at the results. I pretty much do the job in my head, and all I'm missing is a number. I just don't have the scale of the contours. So while quoting a job, I already know what the actual intelligence is going to be and how reliable it's going to be. All that's just missing is that final number. So anyone setting up a problem for someone else should be doing the same thing. Imagine you're looking at a plot of the results and roughly it's a certain shape and there's all that you're missing is those contour numbers. So imagine that point of the project. Don't use simulation as information gathering, use it as a calculator to get to a usually single number.
And how about in terms of finding the right simulation partner?
It's a difficult task. I think you have to go by recommendations. Even to this day, I can't sit down with someone and in an hour know that they're going to be accurate, cost effective, and well informed.
Hmm.
One of the major skills in simulation, you're going to enter a couple thousand numbers into that database. And if there's a person who has a characteristic where 1 in every 100 numbers is off by a decimal, the person ends up not being a good analyst because you can't find those types of errors. Or if a person's slow, we work a mouse a lot of the time. And if that mouse click takes 3 times as long to navigate, I mean, I hire gamers sometimes and they watch me work and it makes them crazy because I'm so slow. Their mice are flying, their cursors are flying across the screen. And I'm just like, now that's value. It's the speed of working with the interface will determine whether someone's a good analyst. And then the last thing is knowledge. You can, of course, analyze anything, but if you really don't understand, like an example is fatigue. Many people will say, I'll do a fatigue calculation. They do a model. They haven't taken into account the fillet, so they have a sharp corner. They pull the stress from nearby, and so now you have mostly a medianist value. And then they go to an SN curve and they look it up on the SN curve. And I'm like, that's actually not fatigue. It's not useful, because with fatigue, you need knockdown factors, you need surface finish, you need all these other factors. And your answer is going to be wrong by orders of magnitude if you don't take into account these other aspects of fatigue. Not to mention that there's not a fillet radius sometimes in the model, or they're not considering welds, for example, where fatigues are most likely to break. So if someone's missing a particular set of knowledge, then the analysis is not going to be effective. You need those three.
Most mechanical engineers understand the basics of simulations, right? The numerical analysis, and they can pick up an FEA tool and spend a few hours or a few days and kind of learn the interface and understand roughly how to apply boundary conditions, things like that. Muddle their way through. But to what extent is it dangerous, or how often have you seen engineers get in trouble because, like you were just saying, there's all this ancillary information and knowledge that you really need. Maybe, I don't know, maybe 70% of the time you'll get the right answer without having all of this ancillary knowledge and experience, but the other 30% of the time you think you get the right answer, but it's completely wrong because you've missed, you don't know what you don't know. Do you run into that very often?
Yeah, you took the words out of my mouth. That's the unknown unknowns. And as engineers, we're constantly have that box of unknown size. And so people that are tasked with doing FEA maybe don't have a lot of experience with it. They have a large unknown unknowns. And a lot of the work I do, I'm always wondering, am I missing something? Is there something I don't know about spalling or subsurface fatigue, initiation, and this thing's going to break? And in the end, I'm really like, oh, I just didn't know about that kind of physics. I've never, or, fatigue corrosion interaction. If you've never done it, I wouldn't have known to check for it. So it's our jobs to work in that territory of the unknown unknowns.
Yeah.
I'll tell a brief story on that front. And this was back at Honeywell. And I'm actually referencing the individual earlier. I'll say his first name, David, who I thought was just an amazing engineer. I learned a lot from him. And I got my first analysis back. It was a color plot of, I think, a tie shaft stretching. And I come up with an answer, 0.1 inches. Now, there's so many buttons I push in a tool I didn't know. There's no way I believed my answer. I knew enough to not be sure. And I asked him, I said, well, okay, I have a result. I said, how do I know it's right? And he chuckled. He says, well, that's your job. And I was like, well, I don't even know how to check it. I said, I could do some hand calculations. And he shrugged, not in like a sarcastic shrug like you should. He shrugged as in, do what you got to do. And I said, well, I don't know how to do these hand calculators. I said, I'm going to have to bring in like my textbooks from school to like learn how to do this. And he literally just shrugged again and started walking away. And that's when I realized this is up to me to get this right. And if I got to phone a friend, ask others in the next queue, pull out some textbook, compare to other models, get on the internet, you do whatever you have to do. That's how you handle the unknown unknowns.
Even if it means being up until 2 a.m. and finding a sketchy website that charges you $2,500 for
Yeah.
for the solution. Now, it actually reminds me a lot of the early days when I started Pipeline. I had only worked full time for maybe 3.5 years or something. So like I had, a little bit of a foundation, but I was pretty early in my career still. And here I was out on my own, solving engineering problems, doing design work. And there were a lot of things that I didn't know how to do. And fake it till you make it kind of became a philosophy. Of course, I needed to make sure that in the end it actually worked. But kind of like when you took that evaporation project on, you weren't exactly sure how to do it, but you had enough confidence that you could figure it out, and you did. It's the same thing. I had enough confidence that I could figure it out, and then it's exactly what you say. It's your job to know this, to figure out some way to do it, and you just you take whatever resources you can, whether it's calling a friend or talking with an old colleague or pulling out a textbook or whatever it is. But eventually you just find a way to get it done. Be creative about it.
Right. And I didn't know that you'd only had a few years first. That's great. Congratulations on your success.
Thanks.
We had a problem where there was some questionable analysis results, and I'm like, I don't know. I think we need to check this or it might break. And we were going to be around when they actually tested this. It's test hardware, not going to be in the field 10 years, but there would be answers within a year or two, and they'll still know our names. And I said, but if it breaks, this is going to cost them a lot of money. Like maybe it'll be $1 million to recover. And he's like, they got deep pockets. And I was like, it was rarely I have to bite my tongue with my own coworkers. And I like through stilted speech said, I try to spend their money as though I'm spending my own money. Like there's a thing about taking responsibility and realizing if it's a $20,000 failure and you mortgage your house to get this product out because you're starting a company, that's the same attitude that Fortune 100 companies are doing. Like every $10,000, $100,000, $1 million is still $1 million.
Yeah.
So
Yeah.
it's often when I'm looking at a project and I think, will this work? I think, okay, if you started a business and this was your money, what would you do? How much would you spend on simulation to get the answer right? And sometimes that means more, and because I can't be wrong. And sometimes it means less, as in, we've done enough.
Yeah. That's a great partnership attitude. That is the kind of attitude that I would want to hear from people I work with. You mentioned Fortune 100 companies. One of the questions I wanted to ask you was, are there things that these giant companies with endless resources are doing with simulation that smaller companies might not be doing, but that they could if they knew to do them?
Hmm. Maybe not in the way that you're asking in terms of applying optimization or more advanced material categorization tool sets. There's some of that, but most of the cases, the things that they're with people with deep pockets that are spending money on, only large corporations would really be able to take advantage of that. So I don't think there's a lot of low hanging fruit in terms of the tool set. Everyone should be growing into the tool set, be aware it's capable, and each year be using more of the tools than before. But it's not like there's some amazing feature that if only they turned on, everyone would like parameterize their work and click solve, and suddenly nothing really works like that. But what they are able to do is to set up mentorships and training and partnerships and documentation and things like that. A lot of companies will end up with a single FEA expert or a couple, and they get siloed and isolated, and there's no one new being trained in underneath, and they're not bringing in outside expertise. This happens more in FEA. That can happen anywhere. It happens more in FEA than anywhere because of the Moore's law that I mentioned, because of the rapid growth of this tool set. Most of the leaders, when I talk to them, they say, no, we know we're amazing at FEA because we're doing so much more than we did 3 years ago. And that's more than they did 3 years before that, because it's exponential growth. And after 10 years, they're actually super far behind, but they're so far ahead of where they were, they don't recognize that, no, actually you can fall behind while having amazing advancement in your in-house tool set.
Interesting. What are some of the capabilities of the tool set that are available to engineers now that maybe 5-10 years ago just weren't an option? Like what are some of the more dramatic improvements that you've seen?
Well, for common accessibility, the contact and prediction of friction has gotten much better. It used to just be an undertaking to try to do anything nonlinear, and more stability has been added. And a lot of times people haven't adapted that. They're still doing static bonded simulations, and it's often time to add the extra accuracy you need it.
Nice. Okay. Have you ever had to deliver results to leadership that weren't what they wanted to hear? And how did you handle that conversation?
Yeah. Most of the time, everyone wants to hear. And we try to give enough exposure as we're uncovering things like a mystery. We don't just come to the end and be like, so and so murdered so and so. That wouldn't be great. We bring them along for the ride, and so they can see it coming.
That's great. Great marketing.
I guess, yeah, it's just kind of our natural process. I will tell you, once we found in an analysis a divide by two error by the original engineer, amplitude versus range. And it took a long time to do it. Nothing was working right. Eventually, I'm like, how do I get their numbers? I got to that person's numbers by sticking a divide by two error. And then I recognized it propagated and actually was the impetus for a product recall.
Oh,
Us
no.
doing the work at all. They basically had the wrong material properties in production and were doing this massive recovery effort and analyzing every product to see if they could keep it in the field or not, because they had this inferior material property, and I was just put in on product number 4 after they'd done like 3 of them. And when I got to it, I'm like, no, actually, your products are better. This change material property means you're getting a better fatigue life, not worse.
No. Uh,
Yeah,
well,
it was not well received. Not by the guy who did the divide by two error, I'll tell
yeah,
you
not for that guy, right?
that.
Wow, that would be an awkward conversation to have. Hopefully that guy wasn't in the room when he had to have the conversation. All right. Well, Rod, I think we'll wrap things up here. Final question for you. You've provided us with a wealth of knowledge and information about simulation. Thank you for sharing all of your insights and wisdom there. What can the community listening to this episode do for you? Is there a technology that you're trying to learn about, or a subject matter expert that you're trying to meet, or a vendor that you're trying to find, anything like that? And the hope is that all of the listeners who download and consume this episode hear your request and think to themselves, I know how to help Rod. I'll reach out to him on LinkedIn.
Yeah, that's a terrific offer, and I would jump at that opportunity. When we talk about, phoning a lifeline, asking others for help. We were talking earlier about, when my associate told me it's your job to figure it out. In my career, I learned the best way to do this is to go ask somebody who already knows. It's much more reliable. And so we do that, and we're constantly in new physics, and I'm constantly trying to look up a person on LinkedIn or I have a folder with names and skill sets where I'm like, I just want to ask somebody who understands creep of copper at very high temperatures. I know that person exists somewhere, someone who's specialized in it. If I could just find that person, I'll pay for their time and they can help us with our current problem set. So if you have a niche skill, it wouldn't be surprised if it's something I would love to have in my file and someday be able to reach out to you and, like I say, pay for the time and learn from you and get a chance to work together.
Terrific. Any particular niche skills that you're looking for right now, or just more of a general request?
Oh, so many. Actually, yeah. Like I need to be able to predict what happens after 20 million impacts of a sphere on a metal surface. I can do a Hertzian prediction, but that type of subsurface falling, you can predict the stress, but now you're talking micro crack fatigue propagation. I don't know if you approach it from a crack theory. I don't know how to do that. 25 million impacts
Of a
is
steel
outside my
ball on
experience.
a surface.
Yeah, it's a different material, but yeah, it just hits a surface. And yeah, I calculated the stresses early on. So, okay, they're below fatigue, well below fatigue. And later I learned, no, it's a statistical flaw size initiation propagation. And I don't know exactly how if that's how I approach it. Like, do I assume a flaw size? Where would I get that flaw size? I have many questions in about a week and a half to figure it out.
Okay. Well, I don't know that we're going to have this out in a week and a half, so we might miss
Oh,
that one.
all right. I'll let you know how it went.
But if you don't find the expert and someone listening to this knows how to do that, reach out to Rod anyway, and he can put you into his book of expert consultants to call on later.
Yes,
All right.
thank you.
Well, Rod, thank you so much for being with us today and sharing your stories and your insights. This was wonderful. How can people get in touch with you?
You can go to the Epsilon FEA website. There's a contact form. It goes straight to me. You can also find me on LinkedIn.
Great. And we'll have the link in the show notes, but in case people just want to listen to it, the Epsilon FEA website URL is
EpsilonFEA.com.
easy peasy. All right. All right, Rod, thank you again for being on the show, and good luck with that microcrack propagation problem.
Thank you. Great to be here. Good to talk with you. Take care.
Thanks. I'm Aaron Moncur, founder of Pipeline Design and Engineering. If you liked what you heard today, please share the episode. To learn how your team can leverage our team's expertise developing advanced manufacturing processes, automated machines, and custom fixtures, complemented with product design and R&D services, visit us at teampipeline.us. To join a vibrant community of engineers online, visit thewave.engineer. Thank you for listening.